Today we're going to start our unit on our identical particles. I'd like to start with just two particle systems. So we can describe the two particle system by the wave function psi of R1, R2, and T. These guys should have vectors over them. We can apply the Hamiltonian operator to each of them. So we have h bar squared over 2m, del squared 1, meaning for the first particle, del squared 2 for the second particle, plus the potential, which in general is a function of the two positions and the time. Moreover, if I want to find the probability of particle 1 being located at R1 and particle 2 being located at R2, psi squared, of course, integrated over those two variables. Moreover, I can say that I expect that my wave function is going to be normalized, so I integrate this over all space. And of course, the outcome should be 1. Now, we're going to talk about some ways that we can sort of simplify our endeavors. So first of all, we're going to assume, as we have all along, that the potential is not a function of time, so it's time independent. That allows us to separate variables, and I can write my total wave function for the two particles as some space-dependent psi of R1 and R2 times e to the minus I times e t over h bar, as we've done all along. And it would be such that I can write a separate time-independent Schrodinger equation, like so. Del 1 squared psi minus h bar squared over 2m, or 2 squared psi plus b psi is equal to e psi. And E represents the total energy of the system, so it may represent the sum of E1 and E2. So let's start with maybe the simplest case where we have two non-interacting particles. So if they don't interact with each other, but they're each subject to some external force, maybe they're attached to two different springs or something such as that, I can write the potential as VR1 and R2 as VR1 plus V1 of R1 plus V2 of R2. And I can solve by separation of variables where I can assume a solution psi of R1, R2, that's a product. We'll call it psi sub A of R1 and psi sub B of R2. So if we substitute this assumed solution into the Schrodinger equation, we're going to get two one-particle Schrodinger equations that'll look like this. Minus h bar squared over 2m del 1 squared of psi sub A of R1 plus V1 of R1 psi sub A of R1 is equal to E1 psi sub A of R1. And same thing for particle 2, minus h bar squared over 2m del 2 squared psi B of R2 plus V2 of R2 psi B of R2 is equal to E2 psi B of R2. And it would be such that E, total energy, would just be the sum of the two energies. So this is the very simplest case where I have two particles like that. I expect then that the two particle wave function is it's just a simple product of two one particle wave functions. So I can write, for example, psi of R1, R2 is equal to psi A of R1 times B of R2 times e to the minus, and if I'm going to do this, I e a plus dB t over h bar. And then, of course, I'm assuming that this is going to be capital psi of R1 and T1 times capital psi B of R2 and T, if I put in my time dependence. So the assumption is particle 1 is in state A, particle 2 is in state B, but any linear combination of such solutions would satisfy the time-independent Schrödinger equation. So for example, I could have an equation that looks like this. I can have psi of R1, R2, and T that looks like 3/5 psi A of R and T times psi B of R and T plus 4/5 psi C of R and T psi D of R and T. Let's say R2 and T, R1 and T, like so. This is going to be R1 and R2. So if this is the state, if we're making a, just an example, suppose this is the state that the particles are in, particle 1 definitely depends upon particle 2 in terms of how you can, which state, which particle is in. So for example, if I measure the energy of particle 1, we might get EA with a probability of 9/25, which means particle 2 must have energy E sub B. On the other hand, we might get energy E sub C, in which case particle 2 has an energy of E sub D. So what we say in that case is the two particles are entangled. Entangled states, in this case, can't be written as a product of single particle states. Kind of like two spin 1/2 particles in a singlet state. Make it a little bit more complicated. Let's talk about, suppose these particles are subject to a central potential that, of course, is only a function of R. If that's the case, they only, V of R1 and R2 is only dependent upon the separation between the two particles, or R2 minus R1. A good example of that, of course, would be the hydrogen atom. In general, most particles are subject both to external forces and to mutual interactions. So for example, if I have two electrons, suppose they're attracted to the nucleus, but they also repel one another as well. So I might write, in that case, V of R1, V of R1 and R2 as 1/4 pi epsilon naught minus 2e squared over R1 minus 2e squared over R2. This takes into account the Coulomb interaction, and then with the nucleus, and then e squared over R1 minus R2 squared, which takes into account the interaction between the electrons. We also know that we can, if you remember from statistical mechanics, we can categorize particles as bosons or fermions, and there are ways that the criteria for each, and we'd like to sort of bring that into the discussion when it comes to identical particles. So for example, if I have two non-interacting particles, and let's say one is in psi A of R1 and T, and I will just call it, make it time independent, and psi B of R2. R2, the product psi of R1 and R2 equal to psi A of R1 and psi B of R2 presumes that the particles are distinguishable. But as we know with all elementary particles, they're not distinguishable. You can't tell one electron from another or one proton from another. And so all things look alike. Therefore, all of the same particle look alike. So I have to be, my most general, or most specific, I should say, wave function I can write in that case is to write psi, and I'm going to call it psi plus minus of R1 and R2 is equal to some amplitude A, psi sub A of R1, psi sub B of R2, plus or minus psi sub B of R1, psi sub A of R2. The plus sign gives me a symmetric wave function that applies to particles we call bosons. Those particles have integral spin. The minus sign applies to fermions. Those particles have half-integral spin. They obey the Pauli exclusion principle. Of course, we've been through all of that in the statistical mechanics class. Oddly enough, we sort of glossed over this in the statistical mechanics class, and we're going to do the same thing here. It actually takes relativistic quantum mechanics to prove that there's a connection between the spin and the statistics. We're just going to treat it as an axiom in non-relativistic quantum mechanics. We'll save that good stuff for later, course in field theory, for example. Well, let's do it for instance. Let's talk about a pair of electrons in a system. Let's ignore the Coulomb repulsion between the two. We're going to see that the Coulomb force, the Coulomb interaction, is not the only interaction we have to worry about. Since the electrons are fermions, they always obey an antisymmetric wave function. So I'm going to call that psi sub A, and that's 1 over the square root of 2. And we'll say psi alpha of 1, psi beta of 2, minus psi beta of 1, psi alpha of 2. Alpha and beta in this case symbolize the 3 spatial quantum numbers and the 1 spin quantum number. So we haven't incorporated spin into our discussion today, but we do need to incorporate that into the discussion. I'm going to write psi then as psi of R times the spin wave function chi of S. Okay, so just to allow for the fact that we do have to be conscious of the fact that you have a spatial wave function and then you have a spin wave function. Both the space and the spin eigenfunctions have a definite parity. They're either even or odd functions. But it must be that their product is antisymmetric, which means if the spin wave function is an even function, the space wave function must be an odd function, and vice versa. So for a symmetric normalized eigenfunction, we're going to write that as 1 over the square root of 2 for normalization. I'm going to use psi A of 1, psi B of 2, because now I'm back in just space. I'm not including spin here. Psi A of 1, psi B of 2, minus psi B of 1, psi B, psi B, psi A of 2. Okay, so that's my antisymmetric space eigenfunction. And then my symmetric wave function would look like, so this is my anti, this is my symmetric, psi A of 1, psi B of 2, plus psi B of 1, psi A of 2. What about the spin eigenfunctions? Okay, so if those are the space possibilities, we've got to talk about the spin as well. Obviously, if the symmetric space eigenfunction applies, our spin eigenfunction had better be antisymmetric, and so on. Spin eigenfunctions. I have 4 possibilities. For spin. This is for 2 electrons. I can have a plus 1/2 state, which we call 1, 1, the 1, 1 ket. I can have the 1/2 minus 1/2 plus, or I should say 1 over square root of 2, minus 1/2, 1/2, and I can also have the minus 1/2, minus 1/2. So this corresponds to 1, 0. This corresponds to 1, negative 1 ket. Okay? In addition, there's one more antisymmetric wave function, 1 over the square root of 2, and that would be 1/2 minus 1/2 minus 1/2 1/2. We call this ket 0, 0. This state is referred to as the singlet state. These are referred to as triplet states because you have 3 of them. So if I have 2 particles, I can look at the total spin as the sum of S1 and S2. S1, S prime I should say, is equal to square root of S prime plus 1. And SZ prime is equal to M H bar. And we can say M sub S prime goes from minus S all the way to S prime to plus S prime. S prime itself can be either 0 or 1. So you can think of the addition of spins in a way that's analogous to vector addition. So for example, for the triplet state, when S prime is equal to 1, MS prime equals 1. When S prime is equal to 1, MS prime can be equal to minus 1. Or when S prime is 1, MS prime can be equal to 0. So the singlet state, S prime is equal to 0, therefore MS prime must equal 0. So in this case, the 2 spins are parallel to one another. In this case, they're anti-parallel. So if the spins are parallel, that means that you're in one of the triplet state eigenfunctions. The space wave function has to be anti-parallel, must be anti-symmetric, in order for the total wave function to be anti-symmetric. Okay, let's take this a step further. let's suppose the space variables, or the space eigenfunctions are approximately equal. So psi 1 of A equals psi 2 of A, psi 1 sub B is the same as psi 2 of B. That tells me that psi A1, psi B2 is approximately equal to psi B1, psi A2. This means that the value of the antisymmetric wave function has to be approximately 0. So if the triplet state has similar space coordinates, the probability density has to be 0. This is why they would act as though they're repelling one another. It's got nothing to do with Coulomb repulsion whatsoever. Remember, we put aside Coulomb repulsion. This is all due to the fact that you have an antisymmetric space wave function. On the other hand, suppose we have symmetric space eigenfunctions. So you have 1 over square root of 2, psi sub A of 1, psi sub B of 2, plus psi sub B of 1, psi sub A of 2. And let's say the two electrons have nearly the same coordinates. That would say that I could write this as square root of 2 psi B of 1 psi A of 2. This means the probability density will be twice as large as the average overall space. So there's a much larger probability of finding these electrons closer together if their space eigenfunction is symmetric. So these are going to be closer together, and I'm going to double the probability. So it's probability times 2. This combination, where the probability is 0 if it's an antisymmetric, probability is double if it's asymmetric, is known as an exchange force. It's got nothing to do with a real force. In fact, it's sort of a geometric effect, but it is a true effect, even though we don't measure it as a real force. So if you have a wave function of two identical particles overlapping, the system behaves as though there's a force of attraction between two bosons, but a force of repulsion between two fermions. So as we say, this is not a real force, but it's a consequence. It's a geometrical consequence of the symmetry requirement. This does not exist classically. You would never run into this that way. So for example, let's take the hydrogen molecule. In the ground state, you have one electron in the ground state centered on nucleus 1. You have another electron in the ground state centered on nucleus 2, hydrogen molecule, H2. If the electrons were bosons, the exchange force would concentrate the electrons toward the middle, between the two protons. So that would accumulate negative charge and would attract each proton as well, which would form a covalent bond. But electrons aren't bosons, they're fermions, which means that the negative charge should be shifted to the wings. And what that would do is pull the molecule apart. You say, well, wait a minute. We know that H2 exists, so what's the deal? It doesn't happen because spin is also involved. If we describe the complete state of the electron, some psi of R times some chi of S, that's a different story, because the whole combination will be antisymmetric for a fermion. If you remember the spin discussions, a singlet combination is antisymmetric and joins with a symmetric spatial combination. The singlet state is what we call a bonding state, and the triplet state is what we call an anti-bonding state. You might remember those terms from general chemistry. So we have an exchange force. This is different than the Coulomb force, and it is a function of the fact that we are dealing with quantum particles, the Pauli exclusion principle, and the symmetry requirements for space and spin wave functions. That's all we're going to say about identical particles. We're going to talk about symmetry and conservation laws next.